Hi everybody, I've got another example for you today to help you prepare for the final exam. I've got a roller coaster loop-de-loop, and this problem is going to combine three different kinds of problems together. We've got circular motion, we've got centripetal forces, and we've got conservation of energy. All that in one problem. We've got this neat roller coaster. A roller coaster cart is going to start up here with an initial velocity of 0. We don't know how far up that is yet, though. It will roll down here. It's going to make one complete loop around this loop-de-loop, and it's not going to fall off. It's not going to fall off in here. It is just barely going to hang on there. So the question is, what is the minimum height the roller coaster's car starting position such that it gets around the loop safely? What height does it need to start at to get around the loop safely? Well, I already kind of gave you the hint that this is both energy and circular motion. But this is another problem where you need to begin at the end. So looking at this end state of the problem, you know it's going to be going around there. Well, to figure out its minimum speed going around this loop, you're probably going to have to find something with circular motion. Once you have that minimum speed, there at the top of the loop, you can use that speed to figure out something about the height. So given that speed and height, where must it start? This is how we're going to solve this problem. Well, let's start by looking at what's happening in the loop. There's the loop. We've got a cart there on the loop. It came down from here. It's going around this loop like that, and it's going to leave. We need to figure out how fast it has to be going to not fall off right there. That's the most important thing. We don't want the cart to just go meh, clunk like that. That would be very bad for everyone involved. So how do you think we can start trying to figure out what the minimum speed is for that? What kind of problem is this becoming? Well, it's becoming a circular motion problem. We've got something that is in motion going in a circle. Therefore, it's a circular motion problem. When we encounter circular motion problems like this, or really any kind of motion where there are forces involved, what do we want to draw? We probably want to draw a free body diagram. I want you to think about this for a bit and consider what forces may be acting on this cart. Well, what do you think? If you said that there's going to be a centripetal force on this, you are probably not right. Remember, centripetal force denotes a direction, and it is not really a type of force, it's only a direction of a force. So what forces are acting on the cart here? Well, there's obviously going to be gravity pulling it down like that. There could be a normal force. Which way would the normal force be pointing if there's a normal force on this? Yeah, the normal force would also be pointing down because the track is above it and the normal force always points perpendicular to the surface that it's on. If you put your hand on a table, it's not going to try to pull your hand into the table. It's going to push away on your hand. If you put your hand on the ceiling, your hand isn't going to get sucked up into the ceiling. The ceiling is going to push against your hand. And so if there's a normal force, then it would be pointing down. However, we want to find the minimum speed of this cart as it's going around the circle. The minimum speed on it is going to be when the forces on it are minimized. And we'll actually look at an equation for that in a little bit. But for now, we want the forces on it to be minimized. So if we can find a way of getting the normal force to be 0 on it, then that would mean that it's just barely making its way around the loop. It just barely is able to make around the loop. So given that, what do you think the free body diagram will look like? Yeah, it should look like this. That's the zoom in version. We've got the cart, we've got gravity acting on it, we've got the track, and that's it. No normal force. If there's a little bit of normal force, then it would actually be going slightly too fast. Not too fast, but it'd be going more than its minimum speed. If there's a lot of normal force, that means that it was pushing up on the track really hard, and that'll happen if it's going really, really fast. The slower that you go around the loop, the less normal force pushing on you, because you're not pushing on the track as much when you're going around slower. And so if you're going as slow as possible, you should get the normal force to go to 0. And if you go any slower than that, then you'll actually just kind of plop off the track, and you'll fall off the track, and we don't want that. So we want no normal force there, just the force of gravity. So the normal force is equal to 0 because the car is barely attached. Well, what kind of problem has this become now? It's become a centripetal force problem. Why is that? Yeah, the gravity is pointing in the centripetal direction around this loop. When you're here at the top. Of course, if you're there on the side, then gravity still points down, and centripetal means center seeking, and so down is not towards the center in that case. But when you're at the top of the loop, yes, gravity is the centripetal force. So what do I do with that? Well, I can say that the centripetal force is equal to the mass of the cart times the centripetal acceleration of the cart. This is the net centripetal force is equal to the mass times the centripetal acceleration of the cart. Remember that? Remember all that stuff from infinity ago? We should relearn this kind of stuff, get it back in our heads. What are the centripetal forces acting on the cart? Yeah, just gravity. Now, is gravity going to be positive or negative in this? It's going to be positive because it's pointing inward, and inward forces are positive because centripetal, that is center seeking. So gravity is seeking the center there, so it's going to be a positive force equal to mass times the acceleration. And what can we do there? Well, gravity is our center-seeking force. We've got the mass. The acceleration is v squared over r. This will be very useful. And this will be also on your formula sheet. Okay, what can we do after that? We can replace that with something, perhaps? Yeah, the force of gravity is equal to the mass of the object times the acceleration due to gravity. Now what can we do here? Yeah, cancel out the masses, and I kind of forgot there, but it's just g times v squared over r, and then we can solve for v, and we get the square root of g times r. That gives us the minimum velocity that we need to get around that loop-de-loop. Now we can plug in the numbers, and we get the minimum velocity of the loop is 8.85 meters per second. We return to our initial setup, but we have one new piece of information that we can add to it. That the speed that we're going at, the minimum safe speed to go in this loop, is 8.85 meters per second. So we can add that piece of information right there. We know our initial velocity is 0, our final velocity is 8.85 meters per second. We're looking for this minimum height, and the radius of the loop-de-loop is 8 meters. So, how high do we need to be on the ramp to be going at 8.85 meters per second at the top of the loop? What's going to be the easiest way to solve this? Conservation of energy. Yeah, let's try it. Okay, delta E is equal to W. Is there any friction going on here? I didn't mention any, so we're going to assume that there's no friction. There's no external work happening. Delta E is equal to 0. That means that energy initial is equal to energy final. What kinds of energy do we have initially? Well, at the very beginning, do we have kinetic, potential, spring, rotational? what? Yeah, it looks like we've just got potential energy, gravitational potential energy initially, because the initial velocity is 0. What about at the end? Well, we've got gravitational potential because it's not at the ground, and we've got kinetic because it's going at 8.85 meters per second. Now, could you do this saying that this is just a rotating object? Actually, yes, you can. If you do all the math right, and you say that the energy of its rotation is 1/2 I omega squared, and you say I is equal to mr squared, and omega, well, you'd have to convert this into an omega. You could totally do that, and you'd be totally right. But that's a whole lot more steps, so we're just going to say it's kinetic energy. So, gravitational potential initial is equal to kinetic final plus gravitational final. We can then plug in equations. mg times h min is equal to 1/2 mv final squared, where that's v final, plus mgh final, h final. Which, what is h final? Yeah, 16 meters. Okay. We can cancel out the m's, and I messed up again, but forgive me. And then we can plug in the numbers. We get 9.8 times h min is equal to 1/2 times 8.85 squared plus 9.8 times 16, and solve for h min. Ding, ding, ding. We got it. 20 meters. That was purely by accident. I did not mean it to be effectively exactly 20 meters, but happy little accidents, I suppose.